Hello everyone. The topic of today's lecture is conditional expectation and conditional covariance. To understand conditional expectation and conditional covariance, first we have to understand conditional density functions. So conditional density functions, they are very related concept to the conditional probability that we have already defined in chapter 1. We define probability of event A given B, event A that the probability of event A given event B has already happened is basically the joint probability divided by the marginal probability of event B. So by the same logic, we define conditional probability mass function. Probability mass function of y given x is just joint probability mass function of x and y divided by the marginal probability mass function of x. The same goes to continuous random variables. For probability density functions. The conditional probability density function is just joint PDF divided by the marginal PDF. Okay, so now let's look at the conditional expectation. What does conditional expectation mean? So we are basically trying to answer this question. What is the mean of y if you know the value of the x? Okay, or alternatively, how does mean of y depend on different values of x? And keep in mind that 99% of what we do in empirical research, particularly in economic research, is modeling the conditional mean. Obviously, there are different objects of modeling. For example, financial risk analysts, most probably they are more interested in modeling the conditional mean, condition variance instead of conditional mean. But in economic research, we are mainly focused on modeling the conditional mean. Okay. So now let's define the conditional expectation. Conditional mean or conditional expectation of y given x is equal to this animal. Okay, so it's basically the same thing as the unconditional expectation. In conditional expectation, in usual expectation, what you are doing is you are basically putting the thing whose expectation you want to find under the integral sign, right? And then multiply by you weight it by the probability density function, and then integrate over minus infinity to positive infinity, right? So the same goes here. The only difference is that instead of the marginal density, we are scaling y by the conditional density. And this conditional density is going to be a function of x. Remember that. And then we have another concept called law of iterated expectations that basically tells you that the expectation of y given x, if you take the expectation of the conditional expectation, that is going to give you the unconditional expectation of y. And why does that hold? Let me create some intuition of this. Suppose I'm teaching to two sections. Okay, so I have section 1. In section 1, I'm teaching to say some students whose average CGPA is, so mean CGPA is equal to 2.5, and in section 2 the mean CGPA of students is equal to 3, for example. And suppose that the GPAs, they are uniformly distributed in both classes. So how can I put it in a mathematical way? So we say that, so the expectation of GPA given the section 1 is equal to 2.5. So the section itself is the random variable x, and the expectation of GPA given section 2 is equal to 3.5. Okay, so this is section is x. You can think of this section variable as x and GPA variable as y. Given those GPAs are uniformly distributed, then in that case I can say that the overall expectation of GPAs, the expectation of GPA in both classes that I'm teaching, is going to be equal to 2.5 plus 3.5, right, divided by 2. I'm assuming that in both cases I have uniform distribution of CGPAs. Okay, that is, in the case of uniform distribution, you can find it in this way, but in non-uniform case, you are basically taking the expectation over the expectation of conditional expectation over all values of x. That is the essence of it. So you say that expectation of y given x, and if you take the expectation of it over x's, all values of x's, over all sections, you're going to receive just the expectation of y. Okay, that is the essence. Now we have to prove that. Why is that? Why does that hold? It's very simple. Remember that expectation of y given x is nothing but integral from minus infinity to positive infinity, y times f y given x, right? Y given x and dy. I'm summing over y. All right, now let's put it into a blue box for further reference. Now let's find the expectation of, let me use black color, the expectation of y given x. Yes, so we said that in the beginning, we said that whenever you want to find the expectation of something, we just put that under the integral sign. Yes, so this is the something, this is that something whose expectation we want to find. We want to find the expectation of the conditional expectation. So that is that something whose expectation we want to find is just the conditional expectation itself. So let's put that under the integral sign. So what we are doing is we're going to now the expectation is taken over x's. We're going to multiply that by the probability density function of x's and dx, right? So because here, suppose x is the section, so I am basically summing over sections, right? So therefore expectation is taken with respect to x in the second case. Again, from minus infinity to positive infinity. So now let's replace this animal, the expectation y given x, by its definition, the blue box. We know that expectation of y given x is just y times conditional density times, this is basically integral of y times the conditional density. Now let's replace that. So we can say that this guy is actually equal to fx. Now let me move fx to the to the beginning, times, now the definition of the conditional expectation is just the integral from minus infinity to positive infinity. Let me use a square bracket here. Y times f y given x dy, and then I'm going to sum over x's. And now let's pay attention to one fact. What does this mean? Fy given x is nothing but fxy, we have already talked about that, divided by fx, right? The joint density divided by fx. Now let's replace the conditional density by its definition. Let me use another color. So this is going to be equal to minus infinity to positive infinity fx times the integral from minus infinity to positive infinity y times fxy over fy, and actually fx dx, right? And then I'm going dy and then dx. So what do we see here? Look, I'm integrating over y's, so fx here is not depending on y. So due to that fact, we can take this fx out of the integral, out of the inner integral. So this can be rewritten as, just a second, this can be rewritten as fx over fx, which is equal to 1 times integral from minus infinity to positive infinity, y times fxy, the joint density, integrated with respect to y, and then everything is going to be integrated over x's. So this guy cancel each other out, obviously, right? So what I receive here is, let me rewrite it. So I receive minus infinity, positive infinity, isn't it? Then 1 times, so I don't write 1, maybe I write it just for fun, 1 times y times the joint density dy, this is also from minus infinity to positive infinity, and then dx, right? And this is actually, by definition, this is nothing but the expectation of y, isn't it? So y times the joint density dy dx. I mean, we can prove that this is equal to expectation of y very easily. We can say that this is nothing but, obviously I can change the order of integration in this case, right? So maybe I want to integrate with respect to x first and then with respect to y. I can do that. So I can write it as y times fxy, but I'm going to integrate with respect to x first and then with respect to y, isn't it? But pay attention to one fact. Y itself is, this integral is taken, this integral in blue brackets is taken over x's, isn't it? So it means that y can be treated as constant here, and you can basically take y out of this integration sign, right? So we can rewrite it as integral from minus infinity to positive infinity, y times integral from minus infinity to positive infinity, fxy dx, and then dy. But what we know that this animal here is nothing but the marginal density of y. Agree? So we can go further. We can say that this is equal to integral from minus infinity to positive infinity, y times fy integrated with respect to y. And that is basically the definition of the unconditional expectation of y. Here I have to use uppercase letter, isn't it? So this is the proof. Proof of the law of iterated expectations. Law of iterated expectations. Remember that. Let me put it under the blue rectangle. So what else do we have here? We have talked about it. The same holds for a function. I don't want to derive this thing, but this is basically the same thing. It's going to hold for any in a function, right? Now let's move on. What else do we have here? Okay, we have to talk about conditional variance. Okay, the conditional variance of y given x is defined almost the same thing. It's almost the same thing. It's defined in almost the same way as the conditional. Is defined in almost the same way as the unconditional variance. We know that variance is equal to variance of y is equal to expectation y squared minus the square of expectation, right? So the same goes for the conditional variance. The only difference is that you are basically adding the condition here. Okay? You just add the condition. Okay. So remember that when you're fixing this x to some lowercase x, some specific value, you get a fixed value. I mean, expectation y squared is going to be a fixed value. But here, when you don't fix it, this guy itself is a function, is actually a random variable. Okay, this guy also is going to be a function, is going to be a random variable if you don't fix the capital X to some particular value. So this is called law of total variance, by the way. Law of, let me rewrite it. Law of total variance. Okay. So now let's solve one example. Example 1, what we have here. Just a second. Example 1. Okay. It says we have the joint PDF, which is equal to 2 if this condition holds. Just let me rewrite it. So you have x1, x2. That's equal to 2 if x1 is less than x2 and that is less than 1, and 0 if else, right? Now we have to find conditional probability density function of x1 given x2, right? And then we have to compute, we have to find a conditional mean. So expectation of x given y, x1 given x2. And then we have to compute, we have to get the conditional variance and some probabilities need to be calculated. So now let's proceed in this way. What is the conditional density? The conditional density is nothing but the joint density divided by the marginal density, right? So do we know the joint density? Yes, we know it. Do we know the marginal density? No, we don't know it. So we don't have it. So let's find the marginal density. Meaning, let's find fx2. We can find this fx2 by integrating the joint density with respect to x1, isn't it? So we say 2 times gx1, and x1 goes from 0 to x2. Agree? And that is going to give you 2x2 evaluated within 0. No, actually 2x1 evaluated from 0 to x2, and that is going to give you 2 times x2. So just write it in this way: 2 times x2. Right? Okay, great. Now we have everything, all the information to get the conditional density. So f x1, x2 is going to be equal to what? It's going to be equal to 2 over 2. It's going to be equal to, so the joint density, which is 2 over 2 times x2, which is equal to 1 over x2, if x1 is less than x2. Agree? And 0 if else. Maybe it is better if I delete this part. 1 over x2. Just write 1 over x2 here. Now, it's very easy to get the conditional expectation now. The conditional expectation function is nothing but, so I'm integrating from minus infinity to positive infinity, but you're taking, the expectation of x1, so x1 comes under the integral sign times the marginal, the conditional density, which is 1 over x2, right? And then you have to integrate with respect to x1 because you are finding the expectation of x1. Okay, and we have to integrate from minus infinity to positive infinity, but we know that x1 is actually varying between 0 up to x2. So just replace, plug the correct intervals, and then if you calculate it, this is going to give you x1 squared over x2. You have to evaluate it within 0 to x2 interval, and that is going to give you x2 squared over 2. Okay, that is the expectation function. I'm sorry, there is no square here. So this is just x2 over 2. Okay, great. Now let's move to the variance. The conditional variance. So the variance, maybe I should start from a new page. So variance of x1 given x2 is going to be equal to expectation of x1 squared conditional on x2 minus the expectation of x1 given x2 squared. Now we know this guy, the expectation of x1 given x2 has already been found, but we don't know the expectation of x1 squared given x2. And how can we find that? You see here we want to find the expectation of x1 squared, so that x1 squared should come under the integral sign, definitely. We have to multiply by the conditional density, and conditional density is equal to x2 over 2, isn't it? And then we are integrating over x1. And then it goes from 0 up to x2. So if you evaluate this integral, it's going to give you x1 cubed over 6 times x2 evaluated within these things, and that gives you just a second, x1 cubed over 3 sorry, I made a mistake here. The conditional density here is actually 1 over x2, not x2 over 2. It's 1 over x2, right? So this is going to give you, if we have already found it, you see, the conditional density is 1 over x2. It's here. It's here. 1 over x2. So x1 squared times 1 over x2. So if I integrate, that gives me x1 cubed over 3. And that gives me x1 cubed, so x2 cubed over x2 times 3, which gives me in the end x2 squared over 3, right? So that is the expectation of x1 squared, conditional on x2. Now we're ready to go. You can find the variance easily. Variance of x1 given x2 is nothing but x2 squared over 3 minus, so what is the conditional expectation of x1 given x2? It's x2 over 2, right? So x2 over 2 squared, right? And that gives you what? x2 squared over 3 minus x2 squared over 4, and that is going to give you 12 x2 squared, right? That is the answer. Okay, so we also have to calculate some probabilities. So we have to find probability of 0. So we have to compute the probability that x1 falls within 0, 0, and 0.5 interval. So we know that this is nothing but, it's basically integration from 0 to 0.5 fx1 dx1. But do we know fx1? Now let's see. So we have not obtained x1 yet. We can get a marginal probability using the joint probability, agree? And pay attention to the interval where x1 is defined. x1 is defined within, from 0 to x2, isn't it? So to find this probability that x is in between 0 and 0.5, we have to know the fx1. But fx1 is equal to integral of 2, which is the joint density, times dx2 by basically integrating over x2s, and x2 runs from x1 up to 1. You can check it. So x2 is actually between x1 to 1, right? So let's do that. If you calculate this, this is going to give you 2 times x2 evaluated within this interval, and that is going to give you 2 minus right? Great. So to get this probability, we have to integrate 2 minus 2x2 to x1, right? So that is going to give you 2x1 minus 2x1 squared over 2, isn't it? And we have to evaluate it within this interval. That is going to give you 1 minus 0.5 squared, and if you plug 0, it's 0. So basically this is the answer. 1 minus 0.5 squared, that is going to be equal to 0.75. Okay, that is the probability. Now let's compute the conditional probability. Okay, the conditional probability of x1 being in between 0 and 0.5, but given x2 is equal to 0.75. Okay? So for that, we are basically integrating again from 0 to 0.5, but instead of marginal density, we are going to integrate the conditional density. Now let's look at the conditional density. Conditional density is here, 1 over x2, right? And remember that x1 is in between 0 and x2, okay? So we have 1 over x2, which is the conditional density. And here, instead of x2, we are going to plug 0.75, yes? Times, because we're fixing it at 0.75, times, so this is the conditional density, and that's all, gx1, because we are trying to find probability related to x1, and that is going to give you 1 over 0.75 times x1 evaluated within this interval, and that is going to be equal to 0.5 or 0.75, which is 2 over 3. Okay, this is the answer. Okay, what else? Okay, we have to find the joint probability mass function in this case, in this tabular case. So first we have to fill in the gap. Maybe I have to rewrite it here. That is example 2. So we have y, which takes two values, 0 and 1. And then we have x, which takes 2, 3, and 4, right? And 4. Okay. So this is x. So the probability of 2, 0, I mean x is equal to and y is equal to 0 is equal to 0.2. And then we have 0.4, we have 0.1, we have 0.05 and 0.05. And obviously here we have to have 1, like 0.2. Why? Because the summation of all probabilities should be equal to 1. And only when you equate it to 0.2, you get 1, right? Now let's find the marginal probabilities. So marginal probabilities are going to appear at the margins of the table. So this is basically px of x, right? So what is this? We're going to sum over y values. X can be equal to 2 in two cases, when y equals to 0 and when y equals to 1, right? And then if you sum over y values, you're going to get 0.6. Here you're going to receive 0.3, and here you're going to receive 0.1, and summation should always be equal to 1, obviously. So if you sum marginal probabilities, the sum should be equal to 1. And the same goes for marginal density of y here. So if you sum over x values, so y can take value of 0 in three cases, when x is 2, x is 3, and x is 4. So if you sum, you get 0.35, right? And then here you're going to receive 0.65. Agree? So this is the answer to A part. Now let's move to B part. In B part, we have to get the expectation of x. We know that that is basically summation of our x values of x times the probability mass function. And here x takes 2 with probability of 0.6 plus 3 with probability of 0.3 plus 4 with probability of 0.1. And if you do that, you're going to receive 1.2 plus 0.9 plus 0.4, and that is equal to 2.5, right? That is the expectation. Now let's move to C part. In C part, we have to evaluate variance of 2x, which is equal to 4 times variance of x by definition, by the property of the variance. So here we have basically to define what variance of x is. That is going to be equal to expectation of x squared minus the square of the expectation of x, right? So we know this guy is equal to 2.5, but we don't know this guy. Now let's find that. What is expectation of x squared? That is equal to 2 squared times, so 2 is taken with probability of 0.6 plus 3 squared is 9 times, the probability of 3 is 0.3 plus, then the next value is 4, so 4 squared times, what is the probability of 4? That is equal to 0.1, and in the end you should receive, let me see, yeah, in the end you should receive 6.7. So this means that, so the variance of x, variance of 4 times variance of x is actually equal to 4 times, 6.7 minus 2.5 squared. Then this is arithmetic, you have to calculate that. Okay. Great. Now let's move on. What else? We have to find the expectation of x plus y. So what you can do, you can actually split it in two parts. One way is to split it in two parts to write this expectation of x plus y, or you can use the joint PDF, which is joint probability mass function, and just calculate it straight away. Okay. So now let's go this simple way. We know the expectation of x, but we don't know expectation of y. Remember, expectation is a linear operator, meaning that whenever you have some linear, when you have some additive formula, you can apply the expectation on each part of this addition separately. Now expectation of y is taking the value of 0 with probability of 0.35 plus the it takes the value of 1 with probability of 0.65. And that result is equal to 0.65, right? So that is the expectation of y. Therefore, the expectation of x plus y is going to be equal to 2.5 plus 0.65, and that gives you 3.15. All right. Alternatively, you could just calculate it using the joint probability mass function. Okay. Now let's move to E part. In E part, we have to calculate expectation of x given y is equal to 1. So fix y to 1. So let's look at this. So y takes the value of 1 in 3 cases: when x is 2, when x is 3, and when x is 4. So we're going to get the conditional PDF. So what the conditional PDF is? First, we have to define this, right? So that is nothing but it's going to be equal to joint probability of xy. So let me fix y. That is going to be easier. So y is equal to 1. In that case, that is much simpler. So whenever y is 1, x can take value of 2 okay, the joint probability of x being equal to 2, given that, so the joint PDF is 0, the joint probability is 0.4 here, right? So this is the probability that x is 2 and y is equal to 1. Remember, we have fixed y to 1. So this is 0.4. Okay, 0.4 divided by, we have to divide the probability of y being equal to 1, right? Because that is the definition of the conditional PDF, conditional probability mass function. So the probability that y is equal to 1 is equal to 0.65. So this is 0.65. So if x is, if lowercase x is equal to 2, so by the same token, the joint probability of x being equal to 3 and y equal to 1 is 0.2. Then you have to divide it by the marginal probability of y being equal to 1, because we are fixing y at 1. So if x is equal to 3, and then we have again we have 0.05. This is the joint probability of x being 4 and y being 1. So it's going to be 0.05 divided by 0.65 if x is equal to 4. Obviously, we are fixing y at 1 at this in this case. So now if you want to find the expectation of x, given y is equal to 1, that is going to be equal to, you have to sum over x's, because you are finding the expectation of x's, the conditional probability mass function, right, times each value of x. And here the first value of x is 2. 2 is taken with probability of 0.4 over 0.65 given y is equal to 1, plus the next value of x is 3. Okay, so x takes the value of 3 with probability of 0.2 over 0.65 given y is equal to 1, and the next value is 4. The value of 4 is taken with probability of 0.05 over 0.65 given y value equals to 1. So if you calculate it, this is going to be approximately equal to 2.46. Okay, that is the solution. Okay, so maybe I have to use red color here. So this is E part, this is G part, then you have C part and B part and A part. What else? Let's move to example 3. So we are given the conditional PDF, y given x, and we are supposed to find the conditional PDF of x given y. Okay, so now this is example 3, right? 3. Let me copy. So we are given f y given x equals to 2y plus 4x over 4x plus 1, and we are given fx, which is equal to 4x plus 1 over 3, and we are supposed to find fx given y. All right, so for that, to find this thing, we know that this is equal to joint PDF over the marginal PDF, right? But the problem is that we don't know this and we don't know this. Okay, so now let's find that. The joint PDF is nothing but the multiplication of the conditional PDF times the marginal PDF, right? So we can say that, we can replace for that, y given x is 2y plus 4x over 4x plus 1. Then we multiply by the marginal PDF, which is 4x plus 1 over 3. And that gives you 2y plus 4x over 3. Okay? That is basically the joint PDF. Now we have to find the marginal PDF of y. And for that we are going to integrate the joint PDF to y plus 4x over 3 with respect to x, obviously, and we have to know the interval in which x is defined. Let's look at that. So it turns out that x and y, both of them are within 0 and 1 interval. Okay? So if you do that, you're going to receive 2xy plus 4x squared over 6 over 3, right? So 2xy over 3 plus 4x squared over 6 evaluated within these boundaries, and that gives you 2y over 3 plus 2 over 3, which is actually 2 over 3 times y plus 1. Agree? So now let's determine y given x. We are ready to go because we know both particles. We have to divide the joint PDF, which is 2y plus 4x over 3. We have to divide it by 2 over 3, which becomes 3 over 2 times y plus 1. Okay? And that should be equal to, we can definitely simplify it out. If you simplify, you will get y plus 2x divided by y plus 1. Okay. So example 3 is done. Now let's move to example 4. Let me copy it. Okay, this is a bit simple problem. What you have to do is you're given basically expectation of, so you're given the expectation of y given x equals to some x. So I should write it in this way. It basically tells you that this conditional expectation, which should be a function of x, this is actually a constant equal to mu. So for all values of x, you're going to receive the same value for the conditional expectation. So you can fix x at any value and find the expectation of y. So irrespective of the value of x, the conditional expectation of y is going to be equal to mu. All right, now we have to prove that variance of y is actually equal to expectation of variance of y given x. Okay, so here we have to use the law of total variation. Law of total variation tells you that variance of y is nothing but variance of conditional expectation of y given x plus the expectation of conditional variance let me remove it from here, plus expectation of variance of y given x. That is the conditional, this is called law of total variation. You can Google it and see what it is. Okay, so we are given the fact that the expectation of y given x is constant for all values of x. Then we can say that the first term is going to become variance of, instead of expectation of y given x, we write mu. So this is going to be equal to variance of mu plus the expectation of variance of y given x. But we know that the variance of a constant term, so as long as the mu is constant, the variance of constant is 0. Therefore, it is equal to variance of expectation of variance of y given x, right? And that's all. Now let's move on. We have covariance and correlation. Okay, so what is covariance and correlation? Covariance, as the name suggests, it shows you how two random variables are varying. Okay, that is called covariation or covariance. And correlation is almost the same thing. The only difference is that correlation is just the covariance divided by, normalized by standard deviations of x and y. As simple as that. And we do it because we want to get, the covariance is actually, it's not bounded. It runs from minus infinity to positive infinity. And therefore, and it is actually sensitive to units of measurements. And therefore, we are trying to have a measurement. We want to have some kind of measure which is, which is bounded, so that we can compare the relationship, the mutual relationship between several variables. So remember, covariance ranges from minus infinity to positive infinity, but correlation coefficient is always between -1 and +1. And one thing that you have to keep in mind, correlation and covariance, they are measuring the linear association between two variables. Okay, linear association between two variables. So this is the formula for covariance. This is the formula for correlation coefficient. We have several useful things that you have to know it. It's going to be useful in econometrics class. So covariance of xy is just the expectation of xy, the product of x and y, minus the product of expectations. And remember that covariance of xy is the same thing as covariance of y and x. Another useful formula is whenever you have covariance a times x, b times y, where a and b are constants, these constants can basically taken out of the covariance operator. Basically, you can simplify it out a bit, and that is really useful. You're going to be using it in econometrics class. Covariance of x plus y and z, you are basically applying the covariance to this two guys first, and then to these guys first. First, it looks like the a times b plus c. You're basically first finding the product of a and b, and then plus the product of a and c. Okay, remember that. So covariance is somehow alike. So variance of x1 plus x2, that is a very important thing. Remember that. So whenever x1 and x2 are independent, this covariance term is going to get 0 if they are independent. But if they are not independent, so the variance of x1 plus x2, given these two guys are random variables, is equal to variance of x1 plus x2 times plus 2 times covariance. And maybe I have to write it down. I have to say that the variance of x1 plus x1 minus x2 is actually equal to variance of x1 plus variance of x2. Keep in mind, minus 2 times covariance. Keep that in mind. Okay, that's a bit different from addition. Okay, now the key thing, the key message of this part is this. So if this way. If two random variables are independent, remember, independence means that there is neither linear nor non-linear relationship. There is no any relationship at all between x and y, okay? So correlation and covariance, meanwhile, they are measuring the linear relationship between two variables, okay? So whenever you have independence of x and y, it automatically implies that the covariance and correlation is equal to 0. Let me write it. So if independence, then it implies that covariance xy is 0, and obviously correlation is equal to 0, but not the opposite. I mean, this implication is just one-sided, because you might have two variables, x and y, whose covariance is equal to 0, but they might not be independent. It might happen that there is a non-linear, some kind of non-linear association between x and y, but there is no linear association. In that case, covariance and correlation will be 0, but they will not be independent. Keep that in mind. Now let's solve example 5. Let me copy that. So we have fxy equal to x plus y whenever x is in between 0, 1, y is in between 0, 1, and 0 else, right? We have to calculate the correlation coefficient. Okay. So to get the correlation coefficient, first you have to know, that the correlation coefficient is basically covariance of xy divided by square root of variance of x and variance of y. Usually we denote them by sigma, right? So usually we write it in this way: sigma of xy over sigma of x, sigma of y. This is how we write it. Now let's find the covariance. We know that covariance of xy is actually equal to expectation of x times y minus the expectation of x times expectation of y. So for that, we have to calculate the expectation of x first. So that is going to be equal to integral of x plus y. Actually, it's going to be double integral, then 0, 1. So we want to find the expectation of x, so I'm multiplying x by the PDF, join PDF, and then integrating with respect to x and y. Okay, and that gives me what? That gives me x squared plus xy dx dy. So, and x squared xy, and if I integrate, I receive x cubed over 3 plus x squared y over 2, evaluated within 0, 1, and then integrate. So I get 1 over 3 plus y over 2 dy, and if I integrate it further, I receive 1 over 3y plus y squared over 4, evaluated within 0, 1. That gives me 1 over 3 plus 1 over 4, which is 12, 7 over 12. Okay, that is the expectation of x. So in this symmetric case, I don't really need to calculate the expectation of y, because I know that it is going to be equal to 7 over 12 too. Okay, so let me put them within just a second. Okay, let me use another one. So this is the expectation of x. So what about the expectation of xy? Okay, now we have to find the expectation of we have to find the expectation of x times y to calculate the covariance. The expectation of xy is equal to the double integral from 0 to 1 xy times the joint PDF, and joint PDF is equal to x plus y. So dx dy, and if you evaluate this integral, so it's nothing but, let's simplify it a bit, it's going to be equal to x squared y plus xy squared dx dy, and that is going to be equal to now if I integrate with respect to x, it's going to give me x cubed over 3y plus x squared over 2y squared, evaluated within 0, 1, and then this. So if I evaluate, it gives me y over 3 plus y squared over 2 dy, and if I do that, it's going to give me y squared over 6 plus y cubed over 6, and I have to evaluate it within 0, 1, and if I do that, it gives me 1 over 6 plus 1 over 6, which is actually 2 over 6, which is equal to 1 over 3. So we have all the particles of covariance. Covariance of xy is actually equal to expectation of xy, which is minus expectation of x times expectation of y. So we know that the expectation of x times y is equal to 1 over 3 minus the expectation of x is equal to 7 over 12, and expectation of y is also equal to 7 over 12. And if you compute that, it's going to give you 1 over 144. Okay. Okay, now we have covariance. Maybe I have to put it on the square. Okay. And then what else? For computing rho or correlation coefficient between xy, I have to know sigma of xy. So covariance is usually denoted by sigma xy. Divide by sigma x, which is variance, which is standard deviation of x times standard deviation of y. Right? So we need to know, we know it. This is 1 over 144, but we don't know this, and we don't know this. So what is sigma x and sigma y? Let's compute them. Sigma x is actually standard deviation of x, that is equal to square root of variance of x, and that is equal to square root of, so what is variance? Variance is expectation of x squared minus expectation of x, so square of expectations, right? We know expectation of x, but we don't know expectation of x squared, so we have to compute the expectation of x squared. That is equal to we are putting x squared under the integral sign, multiplying by the probability density function, right? And then integrating with respect to x and y. And that gives me what? That gives me, so let me simplify this a bit. X cubed plus x squared y dx dy. If I compute this integral, so it's going to be x to the power 4 over 4 plus x to the power 3 over 3 times y, evaluate within 0, 1, and then integrate with respect to y. So if I do that, I get 1 over 4 plus 1 over 3y. And then I have to integrate them. It gives me 1 over 4 times y plus 1 over 3 times y squared over 2, evaluated within 0, 1, and that gives me 1 over 4 plus 1 over 6, isn't it? And that gives me 12 to the power 3 plus 2, which is 5 over 12. Okay. And the expectation of y squared, I know that due to symmetricity, this is also going to be equal to 5 over 12, so I don't need to compute that. Okay, no need to spend your time in vain. Let me put this, guys, under the integral sign. So expectation of x squared is this, and then expectation of y squared is this. And what else? Now I think we have everything. So sigma of x is going to be equal to square root of, so expectation of x squared is 5 over 12 minus the expectation of x is 1 over 144, and I have to square that. So let me see what the expectation of x is. No, expectation of x is actually 7 over, I'm sorry, I made a mistake here. So expectation of x is 7 over 12. I have to square this thing. And that is going to be equal to 11 over 144. Now let's put it on the rectangle. Maybe I use the green one or blue one, right? Great. Now we know that this is going to be equal, due to symmetricity, this is going to be equal to sigma of y. So I don't want to compute that. So it means that the correlation coefficient between x, y is nothing but the covariance. So our covariance was equal to what? 1 over 144. 1 over 144. Then divide by sigma x is equal to 11 over 144 times. Actually, I have to take the square of these guys. Just a second. So it should be square root of this. So square root of 11 over 144 times 11 over 144. So one is sigma of x and the other is sigma of y. And as a result, I receive you see, I receive 1 over 11 with negative sign. I think I missed something here because I solved it was negative. Okay, I forgot negative sign here. It's negative 1 over 144, right? Covariance. So once you plug it, you receive rho correlation coefficient being equal to minus 1 over 11. Great. Now we have to move on. Let me see what is next. Next we have okay, we have another easy case. We have to show that example 6, we have to show that the covariance between some constant alpha and some x, which is a random variable, is actually equal to 0. It's easy to show that because we know that covariance of alpha x can be written as the expectation of alpha times x minus expectation of alpha, the first term, times the expectation of the second term, right? So if you do that, we know that due to the linearity of expectations, we can easily take alpha out here. We can write it as alpha times expectation of x. And we know that the expectation of alpha is just alpha. Expectation of constant is constant. So we can write it as alpha times expectation of x. And that gives you 0. Okay, that is the solution. Okay, example 7. Example 7. So we have probability mass function of x, which is equal to 1 over 3 if x is equal to minus 1 or x equals to 0 or x equals to positive 1, right? And 0 if else. Right, what we have to do is we have to, we know that there is y, which is actually equal to the square of x, the random variable x. So now we have to show that x and y show that covariance between x and y is equal to 0. So this is a strange case because actually we have already function. There is a map from x to y. Obviously, it means that there is some relationship. But in the end, we get their covariance equal to 0, which means that there is no linear association, linear relationship. Remember that covariance and correlation, they are only about linear relationship. It might happen that x and y, they have some nonlinear, association. And it might happen that at the same time, they don't have any linear association. So covariance and correlation is equal to 0. Now let's show that, okay? Okay, here we have probability mass function of x. Now let's derive probability mass function of y from this. So whenever x is minus 1, x squared is positive 1, right? So y is going to get positive 1. And whenever x is 0, y is going to receive 0. And whenever x is positive 1, it is still going to be, y is still going to be 1. So y receives 1 with probability of 1 over, I should say that y receives the value of 1 with probability of 1 over 2 over 3. Okay, let me start from 0 if x is 0, and 2 over 3 if x is minus 1 or x is equal to positive 1, right? Because there are two cases when y can be equal to, so, okay, let me rewrite it. I should say, so 1 over 3 if y receives value of 0 and y receives the value of 1. Okay, there are two cases when y receives the value of 1. When x is minus 1 and when x is positive 1. Okay, so therefore y is equal to 1 in two cases, and therefore the probability is 2 over 3. Great. Now what we have to do is we have to show their covariance. So show that their covariance is 0, but for that we need the joint probability mass function, right? So let's put the joint PMF in a tabular format. So x takes two values, actually three values, minus 1, 0, and positive 1. And y receives, okay, let me use usual table. It's much better. And so the probability mass function, yeah? So x receives 1, 2, and 3. Agree? And y receives only 0 and 1. So I should say this is x and this is y. Right? Great. So x receives 1, 2, 3. I'm sorry. X receives minus 1, 0, positive 1, and y receives 0, 1. Now let's look at the joint probability. What is the probability that x receives minus 1 and y receives 0? This is not possible because we know that when x receives minus 1, y should receive positive 1. Right? Because minus 1 squared is positive 1. So this is 0. So what is the probability that x is 0 x is 0 and y is equal to 0? Okay? So this is going to be equal to 1 over 3, isn't it? What is the probability that x receives 1 and y receives 0? It's not possible at all. What is the probability that x receives 1 and y receives 1? That is 1 over 3, obviously. What if x receives 0 and y receives 1? It's not possible. If x receives minus 1, y receives 1 over 3, y receives 1 with 1 over 3 probability, okay, isn't it? So now if you sum this, it's going to give you the sum over columns is going to give you 1 over 3, 1 over 3, and 1 over 3. And as a result, you're going to receive 1. And the same going to happen if you sum row-wise, 1 over 3 and 1 over 3. Actually, 2 over 3. The result is also 1. So this is the PMF of y, and this is the PMF of x. Agree? Great. Now let's find the expectation of x. Because we need to show that there is no, and the covariance is 0. For covariance, we have to, the covariance of xy denoted by sigma xy is actually equal to expectation of x times y minus expectation of x, expectation of y, right? So we need to have all these three ingredients. So expectation of x can be found in this way. So x is minus 1 with probability of 1 over 3, 0 with probability of 1 over 3, and 1 with probability of 1 over 3. So you just say minus 1 times 1 over 3 plus 0 times 1 over 3 plus, positive 1 times 1 over 3. That gives you 0, isn't it? Let's look at the expectation of y. Y receives 0 with the probability of 1 over 3 and receives 1 with probability of 2 over 3, isn't it? So it's 0 times 1 over 3 plus 1 times 2 over 3. And the result is 2 over 3. Great. Now let's find the expectation of x times y. This is equal to, so you have to multiply x by y and then by their joint densities, right? So the first case is this. Let's go case by case. So the first case is when both of these guys are 0, okay? Actually, x is minus 1 and y is 0. In that case, the probability is 0. So minus 1 times 0 gives us 0. So let me write all of them. So minus 1, the value of x, times the value of y, 0. This probability that these two will happen together is equal to 0. So then now let's move to the next one. So when x is 0 and y is equal to 0, so when both of these guys are equal to 0. So basically this is 0 times 1 over 3 plus, let's move on. So x is 1, y is 0, 1 times 0 times 0. This probability of these two, probability that x is 1 and y is 0 is equal to 0. Plus, now let's move to the next one. X minus 1, x is equal to minus 1, y is equal to 1. That happens with probability of 1 over 3. So x is equal to 1 times x is equal to minus 1. That can happen with probability of 1 over 3 plus both x and y. X is 0, y is 1. That happens with probability of 0 plus, move to the next one, x is 1 and y is 1. That happens with probability of 1 over 3. 1 times 1 times 1 over 3. And if you calculate this, you can see that it's going to be equal to 0. Okay? So because this guy here is, this guy is 0, this guy is 0, this guy is 0, right? And this guy is 0, and then you get negative 1 over 3 and positive 1 over 3. So now we are ready to compute the covariance between x and y. That is equal to, as I mentioned, expectation of x times y minus expectation of x times expectation of y. And here we got 0. This is 0, and this guy is also 0. As a result, we receive 0. So indeed, although we got some dependence, nonlinear relationship between x and y, given by this function, y is equal to x squared function, but the covariance, the linear relationship between them is not existing. Look at this. So this is an interesting case, because here we got this nonlinear relationship between x and y. X is mapped to y by the quadratic function, but irrespective of this fact, you get zero linear association between them. Okay, so they are dependent, definitely, but dependence does not mean that there is non-zero covariance or correlation. Okay, great. Now let's move to the next question. Example 8. So you have x and y. X is IID. Actually, x and y are IID, meaning that they are independently and identically distributed. Their distribution is the same, but they are not dependent. Okay, they have the same distribution, so are IID, meaning independently and identically distributed. They belong to the same distribution, but they are not dependent on each other. So both of them, mean of x or expectation of x, doesn't matter. Let me use black color. Expectation of x is equal to expectation of y, and that is equal to mu. Variance of x is equal to variance of y, and that is equal to sigma square. Right? Now we have to find correlation coefficient between two random variables. Correlation between z1 and z2. Okay, so where z1 is actually equal to alpha times x plus beta y, so is equal to question mark, where z1 is equal to alpha x plus beta y, and z2 is actually equal to alpha x minus beta y. Right? Now let's do that. So we know that the correlation of z1, z2 is actually going to be equal to covariance of z1, z2 divided by the variance of z1, standard deviation of z1, standard deviation of z2. Okay, now let's start with covariance. So plug for z1, that is equal to alpha times x plus beta times y, and plug for z2, which is alpha times x minus beta times y. So if you compute it, it's going to be equal to, so take first two terms of these two guys. So it's going to be equal to alpha square x square. So alpha square times covariance of x with x plus alpha times beta times covariance of xy plus alpha times beta times covariance of xy again minus beta squared times covariance of y with itself. Remember, the covariance of a random variable with itself is equal to its variance. Okay, great. Now, what do we see here? So alpha square covariance of x with x, alpha beta. Actually, here it should be negative sign, right? It should be negative. Should be negative. Here it should be negative minus, because beta y has negative sign in front. And then plus beta y alpha x and minus beta square covariance of y with itself. So we can definitely cancel this term and this term. They are the same. And what is left is alpha square times variance of x, because covariance of x with itself is just variance, minus beta square variance of y. That is what we receive. Right? So what we need is, we have to find the variance of these two guys, standard deviations of these two guys. So standard deviation of z1 is actually equal to maybe I should start from variance. So this is basically square root of variance of z1. Just plug the definition of z1, that is variance of alpha x plus beta y, right? We know that variance of two terms is basically variance of the first part plus the variance of the second part plus their covariances, 2 times their covariances, but the covariance is 0 because there is IID assumption, so I don't write that to save the space, okay? So I have to take the square root of it. What is more, when I'm taking variance of alpha times some x, I can take alpha out of this variance by squaring it, so I can rewrite it as square root of alpha square variance of x plus beta square variance of y, and then everything under the square root. So this is going to give me what? And due to the fact that variance of x and variance of y are equal to each other by assumption, I will receive that is going to be equal to square root of sigma square times alpha square plus beta square, right? And that is going to give me sigma times square root of alpha square plus beta square. That is what I receive. Okay. So that is the sigma of z1. Now let's look at sigma of z2. Let me change the color. So sigma of z2, let's define the variance, and then we are going to get the standard deviation. So this is the variance of alpha times x minus beta times y, right? We know that the variance of these two, when you have this kind of additive way, you can say that this is equal to variance of alpha times x minus a plus variance of, remember, plus not minus, variance of beta y minus 2 times covariance of x, alpha x and beta y. But we know that y and x, they are IID, they are independent by assumption. Yes, we have already assumed that they are IID. So when we know that when you have independence, then covariance and correlations are going to be 0. So we just cancel it. And what we receive is, we receive variance of alpha x, which can be rewritten as alpha square sigma square of x plus beta square times sigma square, right? Now let's put all these things together. And obviously, if you take the standard deviation of Z2, it's going to be equal to square root of alpha square plus beta square times, sigma times all these things. So this is exactly the same as the variance of Z1, right? So now let's find the covariance. Covariance of Z1, Z2 is just equal to covariance Z1, Z2 divided by, sigma square in this case. Okay, let me write it in sigma Z1 times sigma of Z2. So standard deviation of Z1, standard deviation of Z2. Now let's look what covariance is here. Covariance is just equal to alpha square beta square, alpha square sigma square x. But here remember that sigma square are equal to sigma square x and sigma square y. They're equal to each other. So I can simplify it as alpha square minus beta square. So alpha square minus beta square times sigma square. That gives me the covariance, isn't it? Yes, it's here. Sigma square times alpha square minus beta square. And then divide that thing but by sigma of Z1 and sigma of Z2. Sigma of Z1 is actually sigma times square root of alpha square plus beta square. And sigma of Z2 is also the same. Z2 and Z1, they have the same standard deviation. So I write sigma times square root of alpha square plus beta square. So if you multiply these things out, you're going to cancel. These sigmas are going to cancel. And what you're going to receive is alpha square minus beta square divided by alpha square plus beta square. That is the covariance between these two random variables. That is all. Okay. Now let's look at example Example 8 is done. Okay, now we have the variance covariance matrix. I mean, these are mainly definitions. Here you have moment generator function. Okay, in example 9, you have moment generator function, the joint moment generator function of x and y, and we found that the joint moment generator function is equal to this guy. Great. Now you can get the expectation of x. It can be derived. This is the first row moment of distribution of x. You can take the derivative of this moment generating function with respect to t1 and then set t1 equal to t2 and equal to 0. That is going to give you the first row moment of the distribution or expectation of x. If you want to find the expectation of y, you're going to take the derivative of this thing with respect to t2 and set t1 equal to t2 equal to 0. If you want to get the second row moment, you're going to take the derivative of this moment generating function with respect to t1, but you're going to do it twice. And then set t1 equal to t2 equal to 0. This is the second row moment of the distribution. This is how you can do that. By the same token, expectation of y square, the second row moment of the distribution of y, can be found by taking the second derivative of the moment generator function with respect to t2, right? And then setting t1 equal to t2 equal to 0. Okay. Now, what about this multiplication? What if you want to find the derivative? Actually, what if you want to find the expectation of this product? In that case, you're going to take the derivative of the joint moment generating function with respect to t1, then with respect to t2, and then set t1 equal to 0 and t2 equal to 0. Obviously, this is the same thing as taking the second derivative. I mean, taking derivative, but changing the order of this procedure. So first, if you prefer, you can take derivative with respect to t2, and then with respect to t1. According to the Young's theorem, it should be equal to each other. Okay, so this is how you proceed. Obviously, if you want to get higher, order moments, then you have to take higher order derivatives of this joint moment generating function. So the rest here is, there are calculations. I don't want to spend more time on them. You can try them out, and if you have any question, we can answer. Also, the definitions here, in the final part, these are definitions mainly. You can have a look at them. They're very simple. I don't want to spend any more time on them. Okay, I'll stop at this point and see you in the next lectures.